Tonight's talk by the Institute for Figuring is the second in a two-part series of lectures that look at some of the puzzling questions of our universe through science, art, and mathematics. And the inspiration for these talks is found in the exhibition The Quick and the Dead, which is currently on view upstairs in galleries 4, 5, and 6, as well as outside in the sculpture garden and kind of tucked here and there around the Walker campus. Among many ideas, a concept that emerges from this exhibition is the collegial relationship that art shares with science. Some of the works in the show are, in fact, the latter. The intricate and beautiful drawing by mathematician Anthony Phillips demonstrating the eversion of a sphere was not created as an art object, but as the basis for a set of illustrations on the topic that were published in Scientific American magazine. Harold Edgerton's famous photographs of the slowed movement of objects, such as a bullet piercing a balloon or a glass of milk crashing to the floor, were made as tests with strobe photography in order to document high-velocity events. Hanging on a gallery wall, these works blur the distinction between the two disciplines, or at least allow us to see the beauty in these technical experiments. Science and art have shared a long relationship, propelled by a common sense of curiosity that drives both artists and theoreticians to make sense of things through image and form. One could argue that the two fields are bonded by a relationship of necessity, one giving aesthetic form to the nearly unimaginable ideas of the other, that in turn stimulate innovation through greater understanding. Popular science writer Jonah Lehrer makes this point in a 2000 article in Seed magazine, in which he discusses the breakthrough of physicist Niels Bohr, who in the early 1900s was able to reimagine the structure of matter by studying cubist paintings. In this telling, the visual deconstruction of objects provided by those artists influenced the history of science. This subject is a fitting backdrop for tonight's guests, Margaret and Christine Wertheim, whose organization, the Institute for Figuring, is dedicated to the poetic and aesthetic dimensions of science, mathematics, and the technical arts. Working in the varied arenas of publication, gallery exhibition, lectures, and workshops, the Institute's interests are twofold: the manifestation of figures in the world around us, and the figurative technologies that humans have developed throughout the ages to further our understanding of abstract ideas. Working with mathematicians, physicists, geometers, and science historians all over the world, the Institute conducts collaborative projects that bring complex scientific and philosophical concepts into the plane of popular culture. They have organized an online exhibition about mathematic paper folding, otherwise known as origami, an exhibition and publication featuring a three-dimensional fractal constructed from business cards at a storefront gallery in LA, as well as lectures on knot theory, neuroscience, and the logic alphabet. Their ongoing work with figuring hyperbolic space is an illustration of a beneficial relationship between art and science, or in this case, craft and geometry, as the feminine handicraft of crochet is the tool that finally allowed mathematicians to produce a physical model of the hyperbolic plane almost 200 years after its discovery. And a selection of those models are on view upstairs in The Quick and the Dead. Schooled collectively in philosophy, literature, physics, mathematics, and computing, this duo brings together the sharp thinking of many fields. Margaret is a science writer whose books include Pythagoras' Trousers, a history of the relationship between physics and religion in Western culture, and The Pearly Gates of Cyberspace, a history of space from Dante to the internet. Her writing appears in the New York Times, in the Los Angeles Times, and in Cabinet magazine, where she serves as a contributing editor. Christine is a former painter and a PhD in literature and with a PhD in literature and semiotics from Middlesex University in the UK. She teaches critical theory and feminisms in the undergraduate program in critical studies at Cal Arts, and her writing on aesthetics include essays in Art History versus Aesthetics, Extra, Cabinet, and Open Letter. Whether the subject of their investigation is the sea slug, a snowflake, or an Islamic mosaic, the Institute gives us a rigorous approach to wonder, a territory bravely entered by both scientists and artists to inspire us toward a new way of knowing the world. Please welcome Margaret and Christine Wertheim of the Institute for Figuring.
Thank you very much for inviting us here. It's a real honour for Chrissy and I to be presenting works and to being involved in an exhibition here at the Walker, which is one of the world's great art museums. It's particularly ironic for us in many ways to be here as part of a show that's a big new survey of conceptual art, because what we've done and what we're both going to talk about today was conceived of basically within the framework of educating people, engaging people in wider ideas about mathematics and science. So Christine and I formed the Institute for Figuring and came to it not through the lens of art, but actually through the lens of mathematics and science. And we find it enchanting and wondrous that the art world has been so engaged with our project. This lecture tonight will be essentially in two parts. I will give the first part, which will just introduce the general concepts of what the Institute for Figuring does and what we're about. And then Chrissy will give, as it were, a sort of theoretical framing part that will put it within the context of the art world discourse. And this sort of bipartite nature of the talk, excuse me, I've got a slight cough, mirrors our own backgrounds. Christine and I both represent the arts and the sciences. When we left school, when we left high school, and I should say we're twins, so we left high school together, I went to university and studied physics and mathematics. Christine went to art school and became a painter initially, and then ended up doing a PhD in philosophy, and now teaches in an art school and also works as an experimental poet. So Christine and I's personal lives entwined in art and science is in some sense, I think, a representation of what the Institute is as an organisation. And I think that it is our dual skills and our dual backgrounds that made it possible for us to do what we're doing, and for making possible this work, which in a sense people often say, is it art, is it science, what is it? And to which we reply, well, it's all of those things, and why do we have to split them off into separate categories? I think that what we're trying to get at, in one sense, is to propose that the arts and the sciences aren't as far apart, not just methodologically, but also intellectually, as they're often made out to be. So let me give you a very, very brief tour of the Institute for Figuring. Basically, what I'm going to talk about today is the work that we do generally in mathematical areas. And the way that we sort of like to think of it is that what we're trying to do is to prevent mathematics and science as a form of aesthetic and poetic enchantment. And it's a lovely thing, because when some of the curators were giving us a tour of the Quick and the Dead show earlier this afternoon, the word enchantment was one that they found had been very inspiring to them when conceiving the Quick and the Dead. And the idea of enchantment and a sort of magical wonder is one of the platforms which forms the basis of this show. And it happens to be the one that inspired us specifically to do what we do. So the Institute for Figuring is an organisation that Christine and I founded 5 years ago now in our home base in Los Angeles. And the IFF was inspired by this very, very beautiful concept here that was put forward by a Welsh writer named Merrily Harper. And what she said is that it was the duty of artists to enchant the conceptual landscape. Our conception with the Institute for Figuring is the following. I don't know if it can be said that it is the duty of scientists and mathematicians to enchant the conceptual landscape, but one of the functions that math and science do in fact form in our society is that they do this. And so we formed the IFF with the idea that what we wanted to do was to have a framework for helping to bring into public consciousness and awareness and engagement the the poetic and enchanted dimensions of the sciences, the mathematics, mathematical disciplines and technological disciplines. So all of our work is basically with these fields. We don't go and get artists to reflect on discoveries or fields in science. We look at areas in fields like physics, mathematics, geometry, computer science, biology, and we look at things that are coming out of discoveries and theories in those fields from the point of view of them being aesthetically beautiful in their own right. Mechanically, what we do is we put on lectures, we publish small books, we have a very extensive website that is there, which has a great deal of information for those of you who might want to know more. And increasingly, what we do is get invited to be part of exhibitions like the Walker one today, or also just to curate entire exhibitions of our own. I should say, to say that we have an institute does not mean that we have a building or an exhibition space of our own. All of our work is with putting on exhibitions is with larger institutions. The Institute for Figuring actually operates out of our spare bedroom. You put up a sign saying institute and people take you seriously, and before you know it, they think you have things like an accounting department and a publications department. But, so the institute is, as it were, a victim of its own success. People have taken us seriously, which is absolutely delightful. We, by the way, would like to encourage the viralisation of the institutional landscape, and we hope that some of you might be inspired to have your own institutions, because in the age of the layers of printer and the business card, basically anyone can have an institute. You know, you get yourself a letterhead, and before you know it, you're in business. So, and we would actually like to encourage, as it were, a viralisation of the institutional landscape, part of which is to actually really to cause people to question what does any institute mean? You know, the whole concept of institutions and what constitutes institutional authority also underlies what we do, but I don't really have time to go into that in any depth today. But given that this is in the context of an exhibition which is about conceptual art, and a lot of that is actually questioning the notion of what does art mean, it is something that is, for us, very important. In some sense, we're questioning the notion of what an institutional authority is, and to specifically do that within the context of science and mathematics is something that I don't think is undertaken that frequently. These are some of the subjects that we've done exhibitions and events and lectures on over the past couple of years: physics of snowflakes, mathematical paper folding, tiling and tessellation patterns, various subjects in geometry, knot theory, which is a form of topology, computer memory devices, and various aspects of insects anatomy, like how flies fly and how spiders see. All of these are talks that have been given under our auspices by mathematicians, scientists. But as I say, increasingly our time is taken up with giving exhibitions, and all of these subjects that you see here are exhibitions that we've had at galleries and museums across the country, and increasingly we're being invited to have exhibitions around the world. And all of these are based on mathematical topics. I'm going to just take you through the basis of a couple of these exhibitions over the next 10 minutes, or probably 5 minutes, before I hand over to Christine. We can discuss some of these more in depth in the question time if any of you have specific things you'd like to inquire about then. So one of the linking threads that determines how we decide what we're going to exhibit and what it is that we do at all, a linking thread is the notion that we're trying to show that abstract ideas, things that are often thought of in purely symbolic terms, mathematics, physics, a lot of ideas across the sciences, can actually be demonstrated through the material instantiation of physical objects. So we tend to pick topics in which there is a physicalisation, a materialisation of what are normally thought of as purely abstract, symbolic ideas. And for Chrissy and I, what this is about in part is that we believe that through material practices, human beings can literally play with ideas, and that there are forms of knowledge beyond written forms of knowledge, written words, written symbolic equations, what one learns when one goes to university and studies subjects like maths and physics that I did. That symbolic form of knowing and conveying information is only one way of knowing, and there are other ways of knowing that can be, as it were, achieved through the body, through embodiment and materiality. So it occurred to me walking around the Quick and the Dead show this afternoon that in some sense this exhibition is about how to dematerialise ideas. And in some sense what the Institute for Figuring is doing is the opposite. We're trying to rematerialise ideas. And that symbol of the Quick and the Dead, which is basically that sort of mirror-reflected triangle, I think in some sense represents this. It's like you can look at things from both ends and they meet in the middle. So one of the projects that we have done it's our biggest project by far, is to do the subject of hyperbolic crochet, which we just had a workshop about. And this method of crocheting is basically a way of representing a huge area of mathematics, which is called non-Euclidean geometry. And it's a form of mathematics, it's a branch of geometry that underlies subjects like general relativity. But one of the ways that mathematicians have of representing this is with crochet, with a feminine handicraft, which allows us to make models of a particular kind of non-Euclidean geometry called hyperbolic geometry. And this was an incredibly important discovery in the history of mathematics. First of all, that hyperbolic geometry existed. It's an alternative form of geometry to the two kinds that you all know about, which is Euclidean or flat geometry and spherical geometry. In the 19th century, mathematicians came to understand that there was a third kind of geometry called hyperbolic space, but they didn't have any way of representing it, of making models of it. So they had to understand it in purely symbolic terms. And in 1997, the mathematician at Cornell University, Dana Taimina, came along and said, you know what, guys, I can make models of this with feminine handicraft. I can do it with knitting or crochet. You can do it with knitting, but it's difficult. Crochet is the best method. And you can literally make these hyperbolic surfaces in crochet and stitch mathematical proofs onto them. This hyperbolic geometry also underlies the forms that we see in coral reefs. So that very sort of crenellated, frilly look that coral reefs have is specifically because all these organisms are embodiments of hyperbolic geometry. So Christine and I, 4 years ago, started crocheting these forms with the idea of representing or bringing into being a material instantiation of a coral reef in wool. And it was a way to call attention, we thought, to do a beautiful project that would call attention to the fact that coral reefs the world over are being devastated and wiped out by global warming. So we started crocheting this coral reef, and people, much to our surprise, this project has been taken up with a vengeance all over the world. So what started in our living room 4 years ago as a nice little project that would reside at the intersection of mathematics, marine biology and feminine handicraft has now morphed into a global worldwide movement. We've had exhibitions of the project in New York, London, Chicago, Los Angeles, Arizona. It's going next year to Denmark and to Ireland, and it's going to be shown at the Smithsonian, the National Museum of Natural History, at the end of next year. It'll be the first time the Smithsonian has ever, the natural history part of the Smithsonian, has ever shown an art project. It's now, there are people, communities doing this now in every continent on Earth except Antarctica. There are people in Africa doing it, people in South America. And all of this has evolved out of our living room. And I think the reason is because of this, that this is a project that is equal parts higher geometry, material practices of handicraft that are usually made by women, it's ecological awareness raising, it's a community art project, and it's all of these things simultaneously. And I think what it suggests to people is that our disciplinary boundaries are often fairly arbitrary and constructed, and that in fact we don't need to put science in on one side of the equation, art on the other, domestic life on the other, that all of these things come together in this project in very powerful ways that I think speak to a desire that many people have to see interconnection between things rather than disciplinary divisions. I just want to show you, it has become, as it were, a worldwide community experiment, because all the people who come to this actually find ways to, as it were, do their own personal species of hyperbolic crochet corals. So there's a very beautiful way in which the project itself, that as our crochet reef evolves and grows, it actually mirrors the evolution of life on Earth. What started off as very simple, mathematically pure hyperbolic crochet structures is morphing into a growing, diversifying taxonomy. In a Darwinian process, really, of evolution, we have this growing, as it were, tree of crochet life. So I'm just showing you a very, very few pictures. There are thousands and thousands of pictures of this, but you can see how much these forms really do look like living coral species. And what it suggests to us is that there is, as it were, wisdom embodied in material things, that material things like corals and sea slugs actually can teach us things. It took some of the greatest mathematical minds of our culture hundreds of years to understand what, in some sense, corals and sea slugs literally know in their bodies. I'm just going to speak very, very briefly about a couple of other topics that we do. Another subject which is actually known in the organic world is knot theory. Knot theory is a branch of topology. It's how mathematicians formalise literally understanding knots, like literally the knots that you tie in your shoelaces. This has been a subject that's become of immense interest now, because it turns out the DNA and proteins inside living cells wrap themselves into knots. And so there's great hope that actually this arcane branch of mathematics is going to help us to understand the basic mechanisms of life and potentially even some forms of disease which are believed to exist because of misfoldings in proteins. And so mathematicians working in this very arcane area now suddenly find themselves in great demand to work with biologists. And we've had one of the foremost knot theorists in the world, Ken Millett, come and give us talks on this subject. There are many, many different ways of representing knots that mathematicians have devised, and I'm just going to show you some pictures. And this is just to show you that, in fact, a very highly arcane mathematical topic actually lends itself to extraordinary forms of visual representation. These are, some of the many, many different ways that mathematicians have of representing what knots are and how they technically work. And these are not images produced by artists, but I think they're beautiful and powerful images that actually do embody deep and significant knowledge. And mathematicians can read these images and actually, as it were, imbibe the kind of knowledge that they can often also only understand through equations. You can also make this is a sort of a kind of related topic. Another form that mathematicians have come to look at, tensegrity structures, which are also a subject of great interest mathematically and also to architects, because tensegrity structures, basically this is what Buckminster Fuller championed, it's what geodesic domes are. And there's a great deal of interest from structural engineers in trying to understand tensegrities. So again, what was once a very arcane mathematical topic has become of interest because there are physical embodiments. It's also believed that not only is of this to interest to architects, but it is believed by some people that their tensegrity structures are actually underlying what holds up every living cell. A final project that I'll just mention briefly before I hand over to Chrissy is we have done a project with an engineer Dr. Janine Moseley is her name. It was actually her project to build with business cards out of origami a model of an object that is called the Menger sponge. The Menger sponge was the first three-dimensional fractal that mathematicians discovered. It was discovered at the beginning of the 20th century. And historically speaking and mathematically speaking, it's an extremely important fractal object. And Dr. Moseley set out 10 years ago to build a model of this out of business cards. The scale of this object is, it's built out of 66,000 business cards. This model is 6 feet across on each side, and it weighs about 100 pounds. It took 9 years in the making. There were hundreds of people actually built individual cubes. It's made out of 8,000 business card cubes all structurally joined together. Thousands of people all over America actually were taught workshops to do these cubes, and hundreds of them were incorporated into the project. And so this is a project where basically it is a physical spatial object with enchanted properties, but it took enormous amounts of time to bring it into being, and it was also a communal project. And it couldn't have happened without the participation of a community or without the participation of time. So at this point, I will I'll just show you a couple more images of it. We exhibited what our participation in this project is that Christine and I organised an exhibition of it in a gallery in Los Angeles called Machine Project, and it's the only time ever that this object has been exhibited publicly. It ought to be in a museum somewhere as part of somebody's permanent collection. It's an extraordinary and wondrous object. This is just a paper folding object that was basically a hyperbolic. We had an exhibition of hyperbolic crochet in which I devised a folded version of a hyperbolic space that was the catalogue book, and you actually had to make it up yourself. So there are lots of things you can do with paper folding to actually bring objects into being. So at this point, I will hand it over to Chrissy to talk about the overall concept of the Institute for Figuring within the art world side of things. Thank you.
Hi. Margaret stopped slightly short. She didn't quite get through this one particular exhibition, so I'm just going to say a tiny little bit about it. This particular exhibition is currently, it has been for a couple of years, on show in a museum in LA called the Museum of Jurassic Technology, and they have a small chamber in which we've curated the work of this man, Shay Zellweger. And what he has done is the I'm going to call it the linguistic or formal mathematical structure on which all computing is based is a structure that's called logic. Logic is a word that can be used in many different ways, but one of the ways in which it can be used, the technical way, and what people who are called logicians, how they use the word, is to describe a very specific set of formal relationships. And those relationships have been uncovered over 2,000 years of philosophical and mathematical research. And then in the late 19th, early 20th century, those relationships began to be embodied in symbolic languages. And computing was only possible partially because of engineering and developments in technology, but also it was possible because of this work in the development of symbolic languages. But it turns out that the same set of relationships which make up the logical system that is used in computing can also be formalised in a totally different way as what is called a symmetry group. And this is a model of that symmetry group. There are 16, as it were, points in the group, and in this particular model, each each of the points is given a symbol. But underlying those symbols is this 16 symmetry group, which you can play with as a thing in itself, irrespective of its relation to logic. It has been discovered by 6 different mathematician logicians over history that you can do this. And this man, Crochet Zellweger, who was a professional teacher of psychology in a small university in Ohio, came up with the idea himself, and then he later discovered that 6 other people had done it. And he decided to really develop it totally and developed his own fully formed alternative language for logic. And it has very interesting properties. It can't do anything that any other logical language can do, but the virtue is you could teach it to children. And as he himself says, one of the things that the Greeks would be most impressed with if they came back to our culture today is not cars and not rockets on the moon or losing pods behind Mars or any of that sort of thing. The thing that they'd probably be most impressed with is the fact that we can teach what to them is very complicated mathematics to primary school children or even, first graders. The fact that first and second graders can do long division and fractions would be absolutely miraculous to them. I mean, these were high state secrets that you could get killed for revealing to the plebs. And this is because they began to develop notations that enabled people to learn and manipulate the relations and to develop and understand them. So the thing about Shay's language is that because it's got these symmetry properties, it's teachable to children, and he decided to patent it at one point. I'm not entirely sure why, but he discovered that you can't patent ideas. You can only patent a physical instantiation. So he built these physical models in order to be able to patent the idea. So the exhibition that we have is he spent 25 years drawing in notebooks before sort of computers came around. So he's got all these beautiful physical wooden models that look like sort of hybrids of conceptual stroke pop objects, and these incredibly beautiful drawings. And what's interesting about him is that his work is a work of real mathematics, but he did it completely by himself in his garage in his spare time. The subject I actually want to talk about, and so that exhibition is on in LA if anybody wants to go and see it. That was by way of saying that some of the people we work with are doing general mathematical and scientific projects, but they're not always necessarily embraced by the official scientific or mathematical community. However, it's totally legitimate work. But the subject I actually wanted to talk about is a system of early childhood education called kindergarten that was developed in the mid-19th century. And we all use the word kindergarten now to refer to basically preschool education. But in fact, kindergarten was originally a very formal system for both what we would call preschool and what we would now call early schoolhood. And it was developed by a man called Friedrich Froebel, who, amongst other things, has as part of his early sort of part of his own training, he had for a while worked as an assistant to the man who became famous for formally figuring out the structures of crystals. And so Froebel had this training in again what's called symmetry groups, which is like cubes. What's another? Any crystalline, what we know as crystalline forms that have got symmetrical properties. And when people in the 19th century were trying to crystallography was one of many things that were on the boundary between mathematics and science. There were people that were trying to understand crystalline formations from the perspective of the material physics, and people were trying to understand them from the perspective of mathematics as a formal structure. So Froebel had this experience where you can come at the same thing from both a material angle and from both a formal, purely structural angle. And there was at the same time going on in the 19th century, particularly in Germany, and it's a whole tradition that descends from Goethe, of other people developing educational systems based on the generalised idea that the way a child learns is through manipulating forms in material substances. So I'm just going to show you some kindergarten work, and then I'm going to say a bit more about it, because it's easier to see what they did before you talk about it. So this is dictum of Friedrich Froebel, but as I said, kindergarten was a formalised system which actually spread all over the world and got as far as Japan and America and Australia in the early 20th century. It was very, very widely spread, and we know now that a number of early modern, what we would call master artists, including architects, studied at these schools, at Froebeli, at kindergartens, in their very early youth. The Steiner movement, what you call here Waldorf schools, came out of the same general educational pedagogical trend. They're a slightly later development. The thing about kindergarten is that the educational system was very formalised. They had these 10 gifts that were pedagogical toys, some two-dimensional, some three-dimensional, and all the work that the children did was playing with these 10 different, what Froebel called gifts. And they made these incredibly beautiful things, which to us have an incredible similarity with early abstract art. But many of these objects are done in things like the 1860s. And this is what a kindergarten room looked like, that you had the little children sitting around at the tables, and almost all of the teachers were young women aged between 18 and 23. This is a blackboard with kindergarten figures and some of the tools on tables. This is kind of what a kindergarten looked like, but not in a white cube. It would have been in a, whatever building it was in, but they didn't have white cubes in the 19th century. So this is the first gift. These are other gifts. You can still buy them. There's a kindergarten website. In fact, in Korea, they still use the formal kindergarten system. But the real basis of the teaching, which was all done by young women, were these workbooks where they themselves played with the toys, played with the gifts, and developed these incredibly beautiful. These two are made from a gift. I can't remember which number gift it is, but it's strips of paper and you weave them together, and the idea is to explore the forms of what you can do by simply going under and over. So it's an exploration of a certain kind of two-dimensional iterative or tiling pattern that can be embodied in these coloured strips of paper. So these workbooks that these young teachers made, as I said, almost all of which were female, looked like this. They were these concertinaed books that often had hundreds of pages in them, with these beautiful, beautiful demonstrations of what this playing with particular kinds of form instantiated in certain kinds of materials could do. This is by Winslow Homer. This is a kindergarten teacher in America. It was pretty big in America. Frank Lloyd Wright's mother was a kindergarten teacher, and Frank Lloyd Wright went to kindergarten. This one I particularly love because it's the same general idea, but it's using sewing. It's needle with ribbon through it, and there are other ones. There's three-dimensional forms of these as well, but you get the general idea. And these were for inspiration for the children. These absolutely stunning ones were not done by 4-year-olds. And what is interesting is that given that this movement was all over the world, and given that people like Frank Lloyd Wright and Kandinsky definitely went, and there's a few other people we're not clear about, but this work was being done from like 1860 to about 1930, and why don't we all hear about it? But leaving aside the fact that we don't hear about it, the point that I wanted to make about it is that Froebel's idea was that, and this is what comes from Goethe, is the idea that the way that the mind works is through manipulating forms in material space, that is, manipulating forms in time and space. And in order to do that, you have to have them in some physically instantiated thing. You can't just do it in your head. And what happened in mathematics as it developed in the late 19th and early 20th century and got more and more sophisticated, they moved away from manipulating material objects to translating everything into symbolic notations and then just manipulating the symbols. But that means that only those people who've learnt those highly specialised symbolic languages can do it. And then so you get this massive disjunct between the professionals and everybody else. You can do many very, very elaborate things manipulating forms in time and space if they're materially embodied without having any formal mathematical training. You just have to do it. It might take you a lot of time, but it doesn't require specialised training, which is precisely what Froebel's point was and why he said, 4-year-olds could do it, and the same thing with Steiner. But so one of the points about this is that what these people believed that the children were doing and the young women were doing who were their teachers, they were actually, as it were, developing their own cognitive capacities through play. It's actually extremely like music. There's a set of relationships there and you play with them. They are what they are, but you discover them and you discover your own capacities for expression. So it was very similar. And this actually has an analogue in contemporary art, and in modern art, because the classical way of describing early modern history of what's become the official orthodox story of modernist art with a capital M is that abstract art was precisely that, not about resemblances, not about representation of the world, but about a pure playing with forms. The thing about that playing with forms in abstract art, so it's not actually an accident that kindergarten and modern art look very similar. They both arose out of this idea. The difference is that in the kindergarten thing, the idea of playing with the forms is develop your own cognitive capacities, your own capacities for expression, like music. It's not really about the world itself necessarily. But in abstract art, what you're doing is you're playing with the realm of appearances, with the way the visual object is constructed. It's not really about your own cognitive capacities. And what Peter Osborne proposes in the catalogue to the Quick and the Dead is that what we call conceptual art, which started in the late 60s, is a similar thing, but it's playing with material forms in space in order to lead the mind to an encounter with its own cognitive capacities, with its own capacity to conceptualise, and hence to maybe go further than what you'd gone before. So, in a way, if you take Peter's reading of conceptual art as a legitimate one, then you could say that what kindergarten was doing was conceptual art, and it was being done by 4-year-olds and young women in the 1860s. And it's what we're trying to do. Thank you. You want to take questions?
I should just explain one thing that Chrissy left out about kindergarten. Part of the reason why we have spent so much time in this presentation talking about kindergarten was twofold reasons. One is that 3 years ago we curated an exhibition of this 19th century kindergarten work in a gallery in LA at the Art Centre College of Design. And it is the first and only time that this work has been presented anywhere. A dear friend of ours has the world's great collection of this stuff, and he's been trying for 20 years to get it exhibited. And as an enormous pedagogical resource, not just about the history of education, but because his thesis is that kindergarten formed the seedbed of modernist aesthetics, that when you look at what people like Frank Lloyd Wright and Paul Klee and Kandinsky and Mondrian and many, many of the founders of modernism were doing when they were 4-year-olds, what were they doing? They were actually attending kindergarten. And Norman's belief with collecting this stuff is that actually going through the kindergarten training process actually retrained Western minds into the modernist aesthetic. And we put on through the Institute for Figuring with Art Centre College of Design, we curated the only exhibition there's ever been of this. And again, it's one of those things that should be in a permanent collection in some major institution. The other reason why we feel it's important for us to acknowledge the history of kindergarten is because Chrissy and I feel that what we're doing with the institution, with the Institute for Figuring, is kindergarten for grown-ups. That we actually want to present for all people, children and adults, but mainly our audience is adults, exactly the kind of experience that Froebel was offering 4-year-olds in the 1860s. We believe that everyone should have the chance to go to a Froebelian kindergarten. So please open it up to questions, comments. You can disagree, you can whatever.
There will be ushers in the aisles with microphones, and so if you have a question, please leave for a minute.
Please don't feel intimidated.
Hello?
Yeah.
This is a two-parter. The first part has to do with kindergarten, the kindergarten work. To what extent have you taken that into schools? In other words, have you done any workshops or work with schools through that research?
No, we haven't done anything with schools because the Institute for Figuring has no resources.
Yeah.
It'd be wonderful, but we're operating out of our spare bedroom here, and Christine has a full-time job.
So the second question is perhaps a bit more difficult, but to what extent do you think your twinness affects the way that you work with one another, if that makes sense?
Do you want to answer?
I'm interested in the way, in the process of working, I guess.
This is my view. As Margaret once said, being a twin is like being in an arranged marriage with no divorce option. You imagine for yourself what that's like to work with.
I'll answer it in a different way. I think I think there's no question that because Christine and I have a joint she has a background with deep engagement with the art world, and I have a background of deep engagement with the science world. I don't think there's any question that what we do through the Institute for Figuring could have been done with the commitment to both sides, unless it had been done by two people who could really bring expertise from both sides. One of the things about the usual engagement of art and science is that usually what that means is getting artists to reflect on science, and the artists usually don't really know very much about the science, and there's nothing wrong with that. It's just that it's not really an art science. I mean, the sciences are not really given, as it were, equal representation in the art science equation usually. With what we're doing, I think, in fact, we're primarily coming from the science side, but because of Chrissy's background in the arts, she brings a true understanding of contemporary arguments about aesthetics and about the art world and the art world's interests and concerns. And I think that is a rare thing. But I think it's also the case, as Chrissy said, that, people fantasize about the twindom relationship. People think that it's like the Paddy Duke show, that basically twins it's like you just, as it were, get on. But I think, as the Paddy Duke show brilliantly showed, actually having a great twin relationship is like a marriage. It requires continual and very hard work.
There's a woman over there.
My question is, obviously you two at some point separated and went on different paths, one science, one art. So it seems like one person would be very left-brained and one person right-brained.
Who's I can't see who
I
the
can't
person
see where the
is.
person's coming from either. Oh,
Should I be louder,
What-
or?
I mean, this is possibly very
One
unscientific.
said at one point
Yeah.
had to separate.
No, I heard your question. I was just trying to see you.
One on the path to
It-
science, one
it-
on the path to art. So one twin would probably be very left brain, one very right brain. At what point did you two get together and decide, hey, let's see if we can incorporate science and art to come up with some new concept? At what point did you think or see something that was different?
Well, again, I can only answer this from my perspective. This is probably not a scientific answer. I don't believe in the left brain, right brain split at all. We both did science and the science and math stream at school. I wanted to do that too. Just by the time we finished school, I realised that Margaret wanted to do it more than me, and I knew that we had to separate. And we also both grew up doing handicrafts and making our own clothes, so I decided I wanted to do dress design. But then I ended up going to university and doing a degree in, I was a painter for 10 years, but then I went to university and studied philosophy and literature, but I studied logic, which is supposedly the most left brain thing you can do. I mean, I'm not a logician. I was interested in the history of logic, not being able to calculate. So to me, other people might see that, us as having completely different kinds of minds or interests. To me, what's much more overt, if you actually look at our lives, is that we have completely different aesthetics. Not that we have different interests. Margaret likes things that are rigid. Well, that are sort of red and blue and black and white and straight lines, or at least very clean curves. And I like things that look like there was an explosion in a used jumper factory. So it's more negotiating. Negotiating the aesthetics of what we're going to do is much more problematic than negotiating the intellectual ideas embodied in things about which there's usually no quibble.
Okay. A friend of mine recently painted me a picture of fractals, and I didn't really know what fractals were, but she was telling me about how they're widely represented in nature, I understand. I was wondering if you have explored this at the Institute.
Fractals are a huge class of objects that mathematicians, Western mathematicians, began to understand at the very end of the 19th century. And one of the great revolutions in science of the last 30 years has been the understanding from many parts of the sciences, originating with physicists, that fractals are, almost all of nature is fractal. That, in fact, I don't know how much time we want to spend on this topic, but to explain it very simply, fractals are objects that aren't smooth curves. Instead of the classical way of understanding the world.
Well, just describe the Minga sponge.
Yeah, well,
one to understand.
Well, I'll just explain the general concept, but the general concept that's revolutionary about fractals is that the fractals are not objects that are smooth curves like circles and parabolas and ellipses. Fractals are objects that they're like, think of a tree branching, like, you have a bit of a trunk and then it branches into branches and they branch into sub-branches. That is a fractal object. And mathematicians had thought for a long time that the world operated according to smooth curves. And the whole of Western science, from the scientific revolution in the 17th century up until very recently, was trying to understand the world, at least through the lens of mathematics, through smooth curves. And the reason that was important to people was because smooth curves are what you can analyse through calculus. But with the realisation in the last 20 or 30 years that most of the world is fractal-like, you actually have to understand it through a different kind of mathematics. You can't, it means that most of the world, it's not actually operating in smooth curves, so it cannot actually be analysed in terms of calculus. And that was a revolution in thinking that actually really, it's probably one of the most important scientific insights of the last 200 years. And you've all seen those beautiful images of fractals, things like the Mandelbrot set. And they're very beautiful images. And what is extraordinary is that these kinds of processes actually actually underlie most processes in nature.
But no, we haven't, except that exhibition of the Menga sponge, we haven't done anything that's specifically fractular.
But we would, I mean, this is a whole area that we would love to do more exhibitions on, yes.
There was a woman up there that had...
Yes, I studied in kindergarten the weaving that you talked about, and somehow I didn't make any sense out of it. And I feel that the conflict between rationality and freedom is the big difficulty in our conceptualizing. And I was led into mathematics and statistics when actually I had more of a poetic drive in me, and somehow or other over time I have drifted back to a concept I have of morphic memory, and it seems to get into the element of topology where our metaphors are not only connecting sight, but sound and smell. Our senses, our mind is able to link all these together, and I wonder whether that has anything to do with hyperbolic geometry and whether there is a hyperbolic logic that goes along with this.
From the perspective of mathematics, logic is a branch of, it's a branch of maths now. It's one branch of maths, and hyperbolic geometry is a completely different branch of maths. And from the technical perspective, to use the phrase hyperbolic logic, they're just two completely different branches of mathematics. It's conceivable that somebody would discover in the future a relationship between them in the same way that people ultimately discovered a relationship between logic and symmetry groups, which nobody could have ever imagined prior to the late 19th century. I mean, it was not possible. So maybe somebody will discover a relationship between hyperbolic geometry and logic, but there isn't one, nobody's discovered it yet.
Can I ask one more on this? Topology is something that came into my consciousness more recently, and I wondered whether that has anything to do with your hyperbolic geometry.
You can answer that.
Well, the understanding of hyperbolic space and hyperbolic geometry is part of the broader field of mathematics, which is geometry itself. There is a separate field of mathematics called topology, and geometry and topology are two great realms of mathematics. They are different realms, but there are intersections. And one of the things that happened in the late 19th century was mathematicians trying to figure out different languages for describing structure and form. And they gradually came to understand that there were these two different ways of understanding structure and form. And one is what's classically called geometry, and the other led to this new field of what is called topology. So broadly speaking, topology and geometry are both ways of describing formally, through symbolic languages, what a structure, a form, a shape in general is, but they describe different aspects of those things. And they are linked, but there are separate fields as well.
Hi. I was wondering if you had any thoughts or feelings about Wolfram's New Science?
Yes.
Well, you answered that. Splendid book.
I love the book. I think it's wonderful. That said, has Stephen Wolfram reinvented science? He has in his own head. Sorry, before I answer the question, most of you, do you know what the book is? Should I just say? Stephen Wolfram is a bona fide genius. He's the youngest person ever to have won a MacArthur. He's one of those people who published his first, he's an English guy who published his first serious mathematical paper at the age of 14 or 15, I forget which. He got his PhD at Caltech by the time he was 19, and at 20, before he turned 21, he won the MacArthur, which makes him the youngest person ever to have got it. He is a bona fide mathematical genius. And he's made a great deal of money through a computer company that he started, but he used his MacArthur Genius Award to basically say, I'm going to leave the academic world, I don't need them. And he spent the last 20 years working on his own complete reconceptualisation of science, which he published a couple of years ago in a book called A New Kind of Science, which he believed would completely revolutionise all science, every single field of science. And he believed that he would be hailed not just as a new Einstein, but as the new Newton. He compares himself to Newton in his introduction and implies that he will have just as foundational effect on science as Newton had. To my knowledge, no scientific field has recognised this book. The people who seem to take him seriously are architects.
They take anybody seriously.
But he has had absolutely zero effect on the scientific world. That said, I think for my own, Christine and I have a habit of collecting lunatics. And I think Stephen Wolfram is a brilliant lunatic, and for certain reasons that we probably don't have time to go into right now, I think he's done something amazing.
I just want to say that, to me, I mean, I have absolutely no capacity to judge the quality of the man's work, but, like Shay, the guy that developed his own notation for symbolic logic, and he spent 50 years on it. He's got thousands of pages of these beautiful notebooks and models. It's just it's astonishing. It is legitimate, and I can judge that. I don't know about Wolfram, but I don't care if Shay's work was illegitimate. I don't care if it turned out to have some major flaw. What I like about it is, and what Shay himself says, because he discovered it for himself when he knew almost nothing about logic. In fact, he really taught himself logic after he'd invented a theory of it, which is rather bizarre, but nevertheless splendid, I think. But, as he says, I like to discover things for myself. And I think that this kind of work, where people want to develop their own theories about the world and explore the world for themselves and come up with ways of making something understandable for themselves, is absolutely splendid. And, I actually run a class at CalArts. It's called Pataphysics, and the project they have to do is they have to develop their own theory. And I personally think that in the 21st century, everybody should be developing their own theories. It doesn't mean that anybody else should believe in them. Everybody should have their own theory. But, it'd be better if everybody had their own theory, then you tell me yours and I tell you yours. And, I'd say, well, whose theories do I want to, am I interested in? Not because they're the orthodox truth, but because that's somebody else's personal splendid vision of the world. And I don't care about if it's true or not. True in what sense? That you can use it to make a new kind of machine? Well, I'd just rather have the vision and see the way somebody else's mind work. So in that sense, I think Wolfram is splendid. I mean, it has to be said, he also made a fortune from developing a particular kind of imaging computer program. So he could develop his theory because he had at his disposal this enormous mathematical computing power that no private individual except him on the whole planet, I think, has got that kind of computing power at their disposal. So he had this incredible tool. But hey, he made all that money. You know, it's a better way to spend your money than a lot of other things. Oh, well, you tell him that.
Please encourage him.
He's got his own institute. Steve, by the way, just as a matter of one thing Stephen Wolfram has done for the world, he's got a site called Math World. If you want to know, look up any fact about mathematics, go to Math World. It is by far the best place to, you know, not for professional mathematicians, but for, well, I don't know, but for the layperson, it's splendid.
Oh, I just wanted to find out a little bit more about Margaret's career trajectory, and also whether you guys always knew that, or whether the idea of exploring the intersection regions between the hard sciences and mathematics and arts and aesthetics, whether this was always something that you guys had thought about or were aware of.
Your first question, what's my career trajectory? I went to university and studied physics and mathematics for 6 years, and I thought I was going to be, my original thought was that I'd become a research physicist. But I realised after 6 years at university that much as I loved the science, I couldn't psychologically exist within the academic environment of the sciences, at least as it was practiced in Australia 20 years ago. So I decided that I wasn't going to stay within academic science, and I became a science communicator. So my whole professional life has been as a professional science writer, you know, writing articles for magazines and newspapers, and I write books about the history of physics, and I've also written and produced television science programs. One thing I would like to say about my career that I do feel immensely proud of, for 10 years in Australia, one of the things that I did was I wrote a regular column about science and technology, a monthly column for women's magazines like Vogue Australia. And I'm probably the only person in the world who's ever had such a position. I created it for myself, and it's one of the things that I feel most proud of having done in my life. It's far harder to write about a subject like cosmology for Vogue magazine than it is to write for the New York Times. And the reason is because when you're writing for Vogue magazine, the word cosmology is likely to be taken to be, you know, a discussion about eyeshadow, and you have to actually keep the interest of the reader who might have started on the article because they thought it might be about eyeshadow, and you have to try to keep their interest, and they don't know any of the terminology. So it is something that I feel it's what I've thought of as my missionary work. It is often said that we need to have a better scientifically informed public, and I believe we do. But if we're serious about that, we have to stop with the fantasy that we're going to have to wake up in a world where someday everybody has a subscription to Scientific American. It's not going to happen. It's a fantasy. Those of us who care and love about scientists have a duty to be missionaries and to go out to where the people were. And one group of people who need to be brought into the science equation are women. And where are the women? What do they read? Most of them read women's magazines. So that's why I did that. And I started the Institute for Figuring with the same intention, that I thought that the channels for communicating about science were too narrow. Most of my friends are people in the arts world, and they kept coming up to me and saying some version of the following sentence. They'd say, "Margaret, I bought A Brief History of Time. I couldn't get past chapter 1. I really want to understand physics. Please tell me something I can read." And I couldn't. Because although there are many, many great books about physics, they're written for people like me who are already scientifically literate and well informed. And I thought there needed to be ways and channels of communicating about maths and science that were available to people like many of you, I'm sure, who were smart, sophisticated people, but who probably dropped out of science or probably dropped out of understanding science about the same time you became interested in the opposite sex. And I think this is one of the great things that needs to happen in our society. If we are serious about communicating about these areas, we need to start really looking at the needs of the people and how can we communicate with people and not just fantasize that everybody is somehow going to be able to read things like Scientific American. So that's what has propelled everything that I've done in my career, and I simply see the Institute for Figuring as not a deviation from that or a different project. To me, the Institute for Figuring is absolutely at one with me writing books about the history of physics, because it's all about how to open up these areas to a wider audience.
I'm wondering if you might comment or speculate on the reasons that the scientific world has been so slow to pick up on the kind of work that you've been doing.
There is a great deal that could be said about that. I hesitate to say it publicly. I will, well, all right, I'll say some of it. I think there are reasons. It's shocked me to the core of my being that the science world has not supported the Institute for Figuring one whit. All of the money and all of the support that's come from the Institute for Figuring has come from the art world. And we are deeply grateful and deeply surprised. When we started the Institute for Figuring, we thought we'd be invited into science museums, and we thought the art world would ignore us. It's been completely the opposite. The art world has embraced us, and all credit to them, and the science world has utterly ignored it. I think the reasons for that are twofold. And the main one is that the Institute for Figuring is not operating under the auspices of a university or an accredited institution. There's no one in the equation with a PhD in science. There's no Nobel Prize winners. I suspect, and it does shock me, that the science world, as it were, cannot embrace that lack of authority, and that in some sense it is perceived as heretical to be operating outside of the institutions of science. And the funny thing about this is that the scientific world and the mythos of a young scientist is that at the core of science and being a great scientist and making new discoveries is supposed to be the notion of rebellion, in which Einstein constitutes the great archetype. But what I have seen in the science world's reaction to the Institute for Figuring is that there is a deep orthodoxy and, as it were, inability to appreciate things happening outside accredited institutional frameworks, which in my view is the very antithesis of rebellion.
Well, there is another reason. Science money generally goes to what is perceived as research. What we're doing is not, as it were, research in that sense, though it might be in another sense. It's displaying work that's already been done. So it's not, if we were to ask for money, they're not financing new work. And as far as I can tell, the scientific world focuses very much on that. Having said that, I don't know where you draw the boundaries of the science world, because there's obviously all sorts of stuff going on that's not developing new ideas, but it's using old ideas. But that's often using old ideas for to make things that can be sold so there'll be a profit. We're not doing either of those things. In a way, it's more like an archival project. It's, this has been done before, that has been done before, we're bringing it to your attention. Although we don't have an archive, but each of the things that we do, well, except for the coral reefs, in which we've been making our own new thing. But having said that, in defence of the scientific world, we've also come to believe, and certainly I have anyway, but I think Margaret does too, that, we didn't set out to do this, but as a matter of fact, it so happens that quite a few of the things that we focused on, like kindergarten, which, as I said, though, was developed by Freuble, it was all taught by these young women, and they made all of these books and beautiful objects. They're young women and they're working with young children. The Hyperbolic crochet project was developed by a woman. It's using women's handicraft. The Reef project, which is our hugest project, it's, we do have a couple of male contributors, but 99.9% of them are women. And it's a handicraft. Margaret actually once had a friend, somebody she knew in the National Science Foundation, who was trying to help her, and she thought she could get money for the Hyperbolic crochet project. And in fact, what they turned around and said, well, we'd be willing to give money to develop a computer program to generate hyperbolic forms in virtual space, which as it turns out, is nigh on actually impossible to do. There's reasons for that, but I won't go into them. But it would cost, whatever, it would cost a lot of money. But they weren't willing to spend any money on having actual people do it in real time. Which is, there's something about the fact that a lot of what we're about is embodiment, and often stuff that's very close to sort of handmade and crafty, even if it's being made by scientists. But the whole presentation of it, it's like, okay, you take this supposedly impersonal, intellectual, pure, idealised thing, and you embed it in fluffy wool, and our whole framing is kind of like bedding it in fluffy wool and cut out construction paper and small children, and I mean, there's a recipe for disaster. One of my favourite art sayings, I've forgotten, it's an Englishman, I've forgotten it's Cyril Connolly, I think, but I wouldn't bet on that. He once said, the thing that's most anathema to art is a pram in the hallway. Well, where are you supposed to put it? On the back porch? I mean, I think it's the same attitude. What's anathema to these people is a pram, small children and fluffy wool. It's not on. There's a word for all of that, but we won't say it.
Thank you. First of all, I should say I work at the local science museum, and I think we would love to have you, but I can't speak for the whole museum. But also, I'd like to know...
for your department.
And also, thank you for helping me crochet today. You're very patient. But I'd like to know if there are some wide-held scientific misconceptions that you're looking at for your next projects. And I'm hoping one of your answers is evolution, but maybe you have some other topics that you're looking to explore.
Sorry, when you say, are we looking for wide-held misconceptions?
Well, maybe that isn't your approach, but maybe you're looking at scientific misconceptions that you could help explore and explain with your work. I don't know if that's how you approach it.
No, we don't think in terms of scientific misconceptions. I think Christine put it well earlier when she sort of implied that we're interested in the conceptions. We're not interested in misconceptions because, we're interested in the conceptions. We're not really interested in debating the issue of what is true and not true. That said, the Coral Reef Project has a deep pedagogical and instantiated version of evolution. I think I referred to it in my talk, but I'll just elaborate a little bit. one of the things that's beautiful and surprising to us about the Reef project is how it has come to parallel the process of evolution of life on Earth. The project began with very simple, pure mathematical forms produced by a very simple algorithm. Crochet end stitches increase 1, crochet end stitches increase 1. As the project has evolved, what's really happened is that the algorithms producing the individual models have got more complex. So you might say crochet 3 stitches increase 1, crochet 3 stitches increase 1 for a while, then crochet 4 stitches increase 1 for a while. So what's happened is there is essentially underlying all of the different models in the crochet reef. Each one of them, as it were, is underlined by a crochet code that's different for each model. And that as time has gone on, the crochet code and the as it were, taxonomy of the crochet species has got ever more diverse and ever more complex. And just as life on Earth began with very simple protoplasmic seeds and got ever more complex and diverse as the DNA code complexified, so too the Crochet Reef Project has got this algorithmic code that's got diverse and complexified and has literally brought into being a crochet taxonomic tree of life that is ever more diverse, like the Darwinian tree of life. And each person who comes to this can develop their own variations. So someone comes along and develops a whole new kind of strata of things that we hadn't even imagined. So it's literally like they're someone's developing a new, lizards. Someone's just discovered the equivalent of lizards, or someone's discovered the equivalent of marsupials. And so the project has become like a worldwide organic evolutionary experiment. And we see, it's one of the aspects of it that I'd really love to deal with in a science context, because I think this project has become a really powerful way to demonstrate how even with a simple code, you can get amazing structural, taxonomic, morphogenetic diversity.
One of the things about the Reef project is it's not just the code that's developed too. It's the materials, and by materials, it's the literal materials, wool or string or videotape or scientific wire, but also whether you do it really tight or really loose. A lot of different aspects of the actual physical making come into being. But the other thing about the Reef project is that it may be that life on Earth actually didn't develop through evolution. Maybe it was all created one afternoon or 1 week. But the point is, evolution through random mutation is possible because our reef developed like that, and we can prove that. That's true. That's true. Before you all go, can I say, we have some brochures about the Institute for Figuring. I'll just leave them at the front for anybody who might want to take one. But we'll just end, because I know we have to leave this room any minute. I would just like to reiterate the thing that Chrissy said earlier, which is one of the things that we're trying to encourage with the IFF is the notion that there is a diversity of ways of seeing possible. And what we're trying to do is to, in some sense, embrace, encourage, and glorify in the sheer wondrous diversity of the ways it is possible to formally see, through formalized languages and processes, to see the world. And that one of the things that the IFF is really about is as it were, embracing the plenitude of human literal ways of seeing, and ways of representing, and ways of understanding, and ways of knowing. We're not
engage with the question of, is it true? We're interested in the ways in which things are powerful, helpful, useful to human beingness. And I think that is an area of science that sometimes gets forgotten. In the 20th century, I think, or particularly the late 20th century, I think we've become a little obsessed with the notion that science is about truth. There are lots of forms of truth, and there are many forms of scientific truth too. And I don't think that science should become to be seen as purely about some capital T truth. Science is a way of seeing and doing that ultimately its purpose is to benefit our beingness as humans. Let's not forget that aspect of it. So thank you.